Javier, take it away.
Hello, hello, sound checking. Make me a signal if I go too loud. Sometimes I speak very loud. Thank you. Well, thanks to Maya and Stephen for organizing this year's farm. It's really a pleasure to be here. Also, thanks for the reviewers, for the comments, and the program committee for selecting my work. It's really exciting to be here, and the talks so far have been amazing. So, well, what to expect from this demo? It will be half a presentation of the work in progress, which is related to my PhD research, and the other half, maybe not a half, but maybe less, will be showcasing what the RTG library. What?
I'm so sorry. I didn't plug your computer in. That's audio.
This is audio for you. Okay. Okay, so I will cover an overview of the project, the central ideas, and we see some examples. Full disclosure and, what was the other word? Anyway, the system still has many lackings, but I mean, there's a lot of exciting venues of development that I hope to convey to you today. Well, the research context. I have a background in mathematics from my undergraduate studies. Then I started my own practice as a music producer. And afterwards, this led me to pursue a degree in music technology, where I actually aborded technology from a critique point of view. Like, as a user, I was questioned about how does this power technology give me, how does this translate towards like critical comment on culture. And finally, I reached programming language from musical expression, which is my current line of research. Well, the inspiration for this project is mainly derived from two other projects. First, we have Tidal Cycles, which is a community-driven environment for creating algorithmic patterns for live coding. And also Chronomorph, which is an application that is designed to explore well-formed and perfectly balanced rhythms, which in a graphical user interface. Both projects have different affordances, scopes, and user interfaces, and both are capable of generating and transforming rhythmic patterns. Those are the interfaces. One is text-based, and the other one is completely graphical. So when we think about geometry, we usually think about the left side image. So you will see kind of figures in 2D or 3D representation. But I'm interested in how this representation or geometric properties translate into internal structures of the objects being manipulated, which in this case are rhythmic patterns. The design goals for the, well, I forgot to mention, the library is called RTG. We'll see what that stands for, but its design goals is to be a text-based UI and has a terse pattern manipulation as it is intended for live coding. Also, I want to implement smooth morphing between given patterns. And finally, evolving patterns using parameterized geometric properties. These are embedded into patterns, and then they will be used in the implementation background to do this kind of evolving and morphing. Right now, the development of RTG has been mainly focused on these first two elements, as I'm exploring like the feel of the interface for the purpose I want to give it. Okay, RTG stands for rhythm, time, and geometry. So talking about rhythm, it is about applying musical rhythm research to the generation of patterns. I also want to explore implementation strategies to deal with musical time, which I also found fascinating. And finally, which is the main element now that I'm exploring in the interface, is using pattern types with geometric properties accounted for in group operations defining an even geometry of patterns. Groups here are in the sense of algebraic groups. So, you know, this is the very basic structure that you get with sum, multiplication, even the basic isometric transformations of the plane and any kind of space. Okay, so what I want to use geometry for, it will be the framework for rhythmic pattern generation and manipulation towards a declarative, serendipitous, and expressive environment for music live coding. Actually, the serendipitous and expressive can become conflictive, because if you want to express an exact idea, that will be in conflict with the possibility of exploring like non-expected things. And I'm done talking about randomness. So far, I'm not interested in implementing randomness, but unexpected ways of combining patterns. And how I'm going to do that? Well, this will be developing a library based on type-level constraints that guarantee the musicality of the result in accordance to the geometric properties I just mentioned. And the current research scope has to do with Haskell type system, so I'm interested in using types to encode these properties and ensure the transformation and composition of patterns. In relation to rhythm geometry, the implementation of geometric properties as pattern structure, rhythmic grouping, balance, well-formedness. There's a bunch of research, mostly targeted toward analysis of music. So most music theory is about analyzing what already is, but I'm wondering, and my main target is to leverage this knowledge to the generative side, so we can create things on the fly. And also the syntax semantics of domain-specific languages for music. This is a broad scope as well, and I'm interested in like the ergonomics of language when you are writing. Well, I mentioned groups, and the Erlangen program is the conceptual framework that gives sense of groups to be thought as a manifestation of geometry. The legacy of Klein's Erlangen program is the conceptual understanding of groups as encoders of abstract geometric symmetry. And using groups opens the possibility of exploring the mathematical idea of symmetry transformation in the domain of music. This is really an open question for me and has been a leading in exploring sometimes difficult subject, because one central element of a group is to have an inverse of an element. So you will have a pattern, and then you ask, well, what's the inverse of this pattern? And what will be an identity? Because that's a property. If you have an element and its inverse, its operation among themselves gives you identity, which might be silence, which might be a single event. I mean, you have to define it. And some definitions don't give you all group actions. Sometimes they are limited. So this exploration for me is like, okay, if I can give patterns group structure, then patterns can also have an inner geometry, like an inner geometric life inside themselves. If I can't, this what I'm seeing is that geometry in time has certain restrictions. And the interface, you can see some of this in the paper. First, I'm using the standard type class of subgroups. So that operator will be the subgroup operation. And the invert function is used to get the inverse of an element. So you will have, first you need an instance of subgroup, then monoid, and finally you have groups. Groups is just a monoid with the inverse property. And so far, I've been having a lot of fun working these things out, like developing this main interface, which is just a type class. So the last implementation, I set the constraint for the type to be a group. Before, I just wanted to just give me a way to operate the elements. Now I'm trying to force that for the type to actually be a group, for it to become a rhythmic type. So the interface is really simple, and internally what is being done is everything that can be converted to a rhythmic pattern will be a rhythmic type. That's the first to rhythm function. And rhythmic pattern is also the simplest representation of a pattern. I'm thinking about lists. So you will have binary elements represented either a silent moment or a onset moment when a musical event is triggered. Okay, so now I can go towards examples. I actually have, how much time I have left? I forgot to set my timer, and now it seems maybe 10 minutes? Okay. Okay. Well, I have these fallback videos because I never know. Sometimes my laptop is quite old. It has almost more than 10 years. But should work now. First, let me try these videos, and then I can do the live demonstration. I don't know if sound will be working. Wait. That should be going. I just showed you one kind of rhythmic pattern I have, which is time patterns, which are just basically ordered rational number lists. And these lists are eventually always translated to the representation I mentioned about rhythmic patterns. So we have zeros and ones representing both rests and onsets. Now, when having the logic separated by types allow me to define different operations using the same interface for different types of rhythmic patterns. And so far, everything is completely asynchronous. This is one of the biggest lacks of the system. I'm just trying now to test what kind of results I'm getting from the current definitions of the operation. Now, I also have an Euclidean type implementation, which is the common Euclidean rhythms. The third parameter accounts for rotation. And they can also be operated among themselves, with a definition completely different from what you get when you are dealing with regular time patterns. What you just heard, everything so far, is the result of a quick and dirty solution to getting sound out of the patterns, because before that, it was just number list. I mean, before. So I'm just basically using the standard tidal cycles library and sending messages through OSC to SuperDirt in SuperCollider. So in this way, I'm getting sound, but buffering is still not implemented. So this is also fun so far. But what happens is the scheduler is deciding the exact timing of events. So now each event is like if two players don't know anything about each other and are completely isolated soundly, so they will play together for an audience who is actually listening. That's what's happening right now. So there's much work ahead for this part of the time implementation. Wait, there was something else I wanted to comment. Okay. Okay, the last video example. One of the main ideas is to, at least at this point in the design, is to avoid specifying a pattern explicitly. As far as this can go is when you call an Euclidean pattern, you give certain parameters, but it's not like referencing tidal cycles, like having a mini notation where syntax allow you to specify exactly how the cycle is divided. Now we assume patterns are given. So that 5B pattern and that Chico pattern are being combined through a different operation. They are being lifted toward the rhythmic pattern type and then combined. So the idea of the ampersand operator is that so far there are only two different rhythmic pattern types. And as I said before, and this is one of the main points of where the group inspiration has led me, is to have them separated for them to have different operations. Now, when I use the ampersand, they are lifted towards being a rhythmic pattern and then combined using a standard predefined operation. So I can have expression like the last one when the priority is on the type operation. So for example, 5B will be mixed with the Chico rhythm first before being combined with the Euclidean rhythm. So I can decide if I'm going to combine operations using their own group operation or using the standard one. So then I can have combination for all the different types. And that's basically it. Thank you for listening. I will gladly take any questions. Thank you.
Fascinating work. I'm not sure if perhaps I'm the only one in the audience who's not aware of the background. But what is this Euclidean function that you speak of?
The Euclidean function is it's actually called the Euclidean algorithm. It's just an equivalent of it's a Bjorklund algorithm, which what it basically does is takes, like you have a set of ones and a set of zeros, and what it tries to do is to put them in a way that maximizes the evenness of the pattern. Like they are as well distributed as possible. I mean, if the two sets are coprime, then you won't have an even ordering. So you move from even ordering when you have coprime numbers.
No, you had a Euclidean function that took three numbers and produced a time pattern, correct?
Yeah. Yeah, the first number will be the number of events you will have in the pattern. Then the second number is the chromatic universe is called in the context of scales. In the context of rhythm will be like the even division of the bar. So you have an even division of the bar of 8 elements, and then you have 3 events, and they are put inside those 8 places, distributed as evenly as possible. The last parameter is just rotation of this pattern.
So another question that I have, and the last question, is you had 2 operations. There was an ampersand, and then there was the
Diamond, let's call it.
Yeah, the diamond, the Lister pen, the monoid pen, right? So did you define those functions? I missed it.
No, they were not defined here. The definition is actually just suggested on the demo paper, and they are referenced there to the code. Because right now the definition has I actually use the same Euclidean algorithm for pattern. The append function, the common one, is just appending, right? This diamond operator.
So the diamond operation is just appending to patterns? No, that's not.
No, what's happening, I tried that, and obviously it doesn't work that well because you get basically a big mesh of a pattern. But what I'm doing right now is I will take the 2 patterns. They may have different sizes, and I will take the smaller one and match the events, distributing the events as evenly as possible of one into the other.
Awesome, really good, thank you. I have a question. So in your abstract, you mentioned that the technique that you are developing produces or aims to produce interesting rhythmic patterns, which means that somehow you are tying that a rhythmic pattern that is interesting has to do with that Euclidean distribution. Can you elaborate on why is that? Like, how do you understand an interesting pattern? Why is that interesting? Well, not interesting pattern.
That is a direct reference to Toussaint's work, Godfrey Toussaint. He wrote this book, The Geometry of Musical Rhythm, which I drew a lot of inspiration from. And the question is, rhythm has no boundaries. And on actual performance, the time is not mechanical. It is felt, right? But within some of the rhythms that are performed, there are certain regularities, and these regularities appear as rhythmic structure when the patterns are analyzed. So this rhythmic structure, if you, like, what Euclidean rhythms does, they input constraints on the construction of rhythms such that they tend to be good. I mean, this good is obviously a matter of question, but what is argued by Toussaint is that good, at least, would mean that the pattern, for one reason or another, is used among different cultures in different places. This will be the thing. So it leads you to the question of universals in music, which is also a polemic question. But we know that certain things are like felt good, like the fifth. Few people will say that the fifth is not a good interval. It's apparently good because of some reason. But you start leaving these commonly agreed conventions, and then you start getting in a philosophical question. But that's the idea. The idea is to be able to call algorithms that generate patterns that are predisposed to be well-behaved, and then you start playing with them. So right now I can call the Euclidean algorithm or take patterns by name, and these patterns have cultural context. Yeah.
So that's all the time we have for questions.
Okay.
So happy to take any other questions offline. Let's thank the speaker again.
Thank you.